a PhD student and working with MERT and so on the xBGAS project. So my topic is towards cycle accurate simulation of xBGAS. So first I will give an overview of xBGAS project and as a complement to the MERT work, and also I will show our efforts and the tools to implement the cycle-based simulation for xBGAS. So as a quick recap, xBGAS was first proposed by John Nadell from the TCL. He's a founder and the chief scientist. And the design goals are by introducing a set of register files corresponding to the general purpose registers to provide extended address capability. So the extended addressing is designed to be flexible to support multiple target applications and different and system architectures. And it does not rely on any like virtual memory mechanism. So with this extended address space, we envision that xBGAS can be used in the following areas, including the high performance analytic flat addressing, mapping storage tiers into address space, providing global object visibility for in-memory cloud infrastructures, and implementing the security extensions, just as Bert mentioned. And the focus in this talk, so we will implement the partition global address space from the microarchitecture level without relying on high-level complicated software stacks. So what is a partitioned global address space, or PGAS? So it basically provides a global address space that is partitioned across multiple processing elements, and each process element not only can access its own portion of the global address space, but can access the global address space in other Ps. And the right figure gives like a situation that the P can like get local shared access and also the remote access. So this programming model significantly simplifies the parallel programming, so programs can access the distributed memory without the need for explicit memory passing, and programs can write code as if they were using a single shared memory region, and the runtime system will take care of the underlying data movements and the communication. So traditional PGAS is implemented through the messaging passing paradigm, where the underlying software overhead is non-trivial, especially for irregular fine-grained remote memory accesses. So this figure, the right figure, gives the profiling of the get operation in OpenShiMain. As we can see, the proportion of the network latency increase, the payload grows from 1 byte to 1 megabytes. So in case of large requests, the impact of the software overhead is insignificant. The network transfers of larger requests dominated the overall latency. However, many modern HPC applications often have irregular or fine-grained remote memory accesses. In these cases, the software overhead can occupy up to 44% of the execution time. So except for the OpenShiMain PGAS runtime, other runtimes such as the GasNet and Global Arrays, they also experience similar significant software overhead when having small irregular memory, remote memory access. So in light of this, xBGAS implements the PGAS model from the microarchitecture level with some additional hardware components. So the xBGAS extended addressing model is implemented via extended register file that is mapped to the base register RISCV register file. So each general purpose register X has a corresponding extended register denoted as E. So notice that these extended addresses are only visible and executable by the xBGAS instructions. So the extended address serves as logical namespace ID, and the base address in the general purpose register serves the standard address to locate the data in the namespace. So the namespace ID can be mapped into physical node identities, memory mapped file systems, or other storage mediums.
I don't know.
Let me try again.
Could you also be using like mirror disk lace space instead of just trying to a secondary spot?
Let's see. It's weird. Let me just try again. Weird.
Almost.
That's weird. Can I use the old adapter? Sorry about it. Really weird for me. Something out to fix somebody else's problem. Can I use this directly? Yeah. Oh, wait. Oh, I see what you mean. Maybe not. Maybe. Perfect. Nice. Okay, so basically, so the base address is used to locate the data in the namespace, and however, even we have like 128 address capability, we do not need any complicated address translation or 128 data paths. So here we list some the xBGAS ISA. So basically, it is an extension of the base RISC-V ISA, and we have three categories of these instructions. The first one is the remote integer load store instructions, which use the I type and S type of the RISC-V specification. So, for example, we have ELD, which is a remote load double words instruction. We also have a raw integer load and store instruction, which can be encoded like three registers address in the same instruction. And we have a set of address management instructions that will move bits between the general purpose register and the extended register. For those who are interested in this xBGAS specification, please refer to this link. So here's the architecture of the xBGAS design. So basically, we introduced like two hardware. One is the arbiter, and the other is the namespace look-side buffer. So basically, arbiter will route the xBGAS instruction directly to the memory interface, and the namespace look-side buffer contains the mapping between the namespace and the remote node addresses. And so these are only like two hardware components that we introduced in the RISC-V call. So to make the xBGAS programming easily, so we developed xBGAS runtime library. So it provides like functions that mimic the baseline Op-Main interfaces, and it's written in combination of C and assembly. So several functionalities are provided, including the initialization of the runtime, provides get-puts interface, and we also have atomic operations and collective operations interface. So in my next part, I will introduce the xBGAS simulation on SST. So why SST? So SST is a structural simulation toolkit. So basically for many simulators that are using architecture design, they are having the following issues. So many simulators are serial and unable to simulate very large systems, and it has significant performance issues when using different simulators together. So it is not easy to modify the tightly coupled simulations for complex systems, and usually it's difficult to simulate at different levels of accuracy. So in light of this, the structural simulation toolkit is proposed to resolve these issues by providing a set of modulars that can be easily coupled together to simulate complex systems. So basically, SST has two different kind of components. The first one is SST core, which is a backbone of the simulation. It provides utilities and the interface for simulation components, and such as the time coordination, parallel communication. So these functionalities are supported in the SST core. We also have SST element libraries that performs the actual simulation. So we also have several built-in models to simulate the processors, memory, and the network. So our work is built upon the REV-CPU component. So this is also developed by TCL. So it is provides cycle-based simulation capability of the RISC-V core, and it can, like I said, it can be worked with other SST components to implement the full system simulations. So the beauty of this REV-CPU component is that it can load the compiled binaries into the simulation, so which make it run the applications more easy. And the REV-CPU have implemented the base integer RSA and the 4 standard extensions, and it also supports the custom instruction extensions and system calls. So this is architecture of the xBGAS extension on the REV CPU component. Basically, we modify the REV CPU to include the extended register, and also we change the decoder a little bit to make the recognizing the xBGAS instructions. We also introduced a memory interface. We name it remote memory controller. That is handling the namespace loop-side buffer, and also it has 4 queues for managing the outgoing, ingoing requests and responses. So for the memory backend, we also reserved a static memory region for managing the xBGAS runtime metadata, including the PID, the total number of Ps, and also the memory area for implementing the barrier. And we also use this region to manage the shared memory metadata. So this is the xBGAS, REV-xBGAS runtime flow. We have a compile time, the runtime. In the compile time, it's basically link the source code with our library and using the RISC-V GLUT compiler to produce the executables. So we modify the RISC-V GLUT compiler to support the xBGAS-ISA. So in the runtime, the REV-xBGAS CPU can load the executables into the simulation, and then we use simulation configuration files to set up the memory backend. For example, we can use the memory hierarchy as the memory backend, and also we can configure the topology of these xBGAS computing nodes with the Merlin network components. So as a result of this simulation, basically we can have a statistical summary and reflecting the behaviors of each component. So this video gives an example of the get operation. On the left side is the source code. So in this demo, I am only showing 2 Ps communicating each other. In this case, the P0 will request a value from P1 using the xBGAS u long long get operation to do this operation. So here's the like the video. So basically, we print out these internal states of the xBGAS runtime, including showing the touching the remote barrier space, and then we do the remote memory operation, and then we print out the outcomes of this operation. So the second one is the broadcast operation. So we use 8 distinct nodes for this simulation. And in this case, the P4 will broadcast the value to other Ps. So before the broadcast, the each P is initialized with its PID numbers for the value. And after the broadcast, we can see the update values are all broadcasted out. So also you can see like after the simulation, we have like a simulated time reported in the interface. And also behind that, we have like generated a CSV file recording all the details of this simulation. So here are some experiment results that we run with a different number of Ps using various of network topologies, which prove that actually we can simulate a large-scale distributed system using our simulation tool on SST environment. So the summary of our talk, so basically we gave an overview of the xBGAS, and also we talked about the xBGAS simulation on SST, and we introduced the REV-xBGAS CPU component, and we conducted several simulations. So our ongoing and future work includes with utilizing the extended addressability to implement the disaggregated memory, and also we are exploring to see if xBGAS can can accelerate the performance in a file system. And also, as Mert mentioned, actually we can use the extended address to implement the security capability in the distributed architecture. So here, yeah, again, some repos presented in this talk. So if you have any questions, comments, feel free to ask. Yeah, thank you.
Thank you for that. And I wonder if anyone has any questions.
I wonder, in your opinion, if this is bound to the CPU, or if you could move this logic into an MMU.
That's a good question. Yeah. So I believe for the CPU part, we have to kind of have a logic to differentiate the xBGAS instructions. So it introduced a set of instructions architecture in the CPU. And also we have to kind of have some modification on the MMU to include these remote memory operations. Yeah.
Thank you.
Folks, I think we'll probably pause here. We need to be over. So the place.